In this video, we do pretty much what we did in the other videos. We've got f of t. It's a function involving the logarithm of t. And so what we're trying to do is graph this function, graph a couple of its derivatives, and look at the relationship between the first derivative, the second derivative, and the original function. We'll be interested in where the function's increasing and decreasing. We'll be interested in where the function's graph is concave upward or concave downward. But the first thing we do whenever we've got a logarithm in our function, or just in general, before we graph something, is we think about the domain of the function. With the domain of real valued functions, let's say t in this case, the implied domain is all real numbers t, such that we are not dividing by 0, we're not taking the logarithm of a negative number or 0, and we don't take any even roots of negative numbers. Since there are no even roots in here, we don't have anything to worry about there. Of course, this denominator can't be 0, so t is not equal to 0. And whatever's inside the logarithm has to be strictly positive, because we can only take the logarithm of a positive number. So t has to be greater than 0. So the domain of this function is 0 to infinity. Any real number, or any positive real number will work. If I want to take the first derivative, that requires the quotient rule. So we're going to take the derivative with respect to t of natural log of t divided by t squared. We'll call this top function the high function, and the bottom function the low function, and then we'll use our mnemonic to compute the derivative. It's low d high minus high d low over low low. And that d is an operator. It applies to whatever's in front of it. So this derivative of the quotient is the bottom function. That's low. D high times the derivative of the top function minus high, that's the natural log of t, times d low, that's 2t. Rather than writing that to the right, which might look like I'm multiplying that t inside the logarithm by the 2t, I'll put that 2t out front so it looks like a coefficient. That way it's very clear that I'm taking this polynomial and I'm multiplying by natural log of t. And then we're dividing all of that by low low. And so you've got t raised to a power, and we've got one of our exponent properties. All we have to do there is multiply those exponents together. So t squared, quantity squared is t to the 4th. One of these t's will reduce, and we end up with t minus 2t times natural log of t. Now to simplify this, we look at this expression and this expression, and we say, do they have anything in common? And say, yes, they have a t in common, so you can factor that out. This is t times 1, this is going to be my first term, and t times negative 2, natural log of t, is my second. And one of those t's will reduce with one of those, so we end up with 1 minus 2 natural log of t divided by t cubed as our f prime. So f prime will equal 0 whenever that numerator is 0 and the denominator is non-zero. Now on the domain, t cubed is always positive, because if t is positive, t cubed is positive. So f prime will change signs when f prime is 0, and then we can figure out whether it's positive to the right of that 0 or negative to the right of that 0 and vice versa. So I will say f prime is 0 when the numerator is 0 and the denominator is non-zero, but we already know it's non-zero in this case. And then we can add 2 natural log of t to both sides and then divide by 2. And then exponentiate. So t is actually the square root of e. So f prime is 0 at the square root of e. And f prime is this 1 minus 2 natural log of t divided by t cubed. And we're only interested in the interval from 0 to infinity, and because that's our domain. Now, t cubed is always positive. This 1 minus natural log of t does change signs at square root of e. We just have to figure out whether it's positive or negative, the left of square root of e. So I'm just going to figure out first where it's positive. And I'll say that expression is positive when 1 is greater than 2 natural log of t. Divide by 2. And then exponentiate. So that's when square root of e is greater than t. Well, square root of e is greater than t when t is less than square root of e. So this factor is positive when t is less than square root of e. So we'll have a positive sign here. And then if all of those were less than signs rather than greater than signs, then all of these would be less than, then this would be greater than. So when t is greater than square root of e, this would be less than 0, which would make this expression negative. So we've got a positive divided by a positive, which is positive, and then a negative divided by a positive, which is negative. Now this chart tells us that our function is increasing on this interval from 0 to square root of e, and decreasing on the interval from square root of e to infinity. Now, square root of e was a 0 of the first derivative, so that means it's a critical point of that function. Since our derivative changes from increasing to 0 to decreasing there, we have a relative maximum at square root of e. So we can infer the f of square root of e is 1 minus 2 natural log of, oops, that's not f, sorry. That's natural log of square root of e divided by square root of e squared. That is natural log of e to the 1/2 divided by e. And with this natural log of e to the 1/2, you can simplify it by saying, well, e to what power is e to the 1/2? Well, that's just 1/2. We're dividing by e. So that simplifies to 1 divided by 2e. So this is a relative maximum by the first derivative test. And the first derivative test just says, if f prime changes signs at a critical point, then that critical point represents a relative min or a relative max. If it goes from positive to negative at that critical point, it's a relative max. If it goes from negative to positive at the critical point, it's a relative min. And if it happens to be 0 at the critical point, then it sort of looks like that sort of hill or an upside down parabola. If it happens to be 0 at the critical point and it goes from decreasing to increasing, it's just going to be a parabola facing up rather than a parabola facing down. So in this case, we've got that parabola facing down, like that's sort of the shape of the graph in this vicinity of square root of e. And so our f of square root of e is a relative max. Okay, so we know that that's true. And we can use that to graph our function now if we want to. And our function f of t is natural log of t divided by t squared. So this will equal 0 when the numerator is 0, and the numerator is 0. Sorry, I'm getting a glare from the sun. The numerator is 0 when t equals 1. Square root of e is the square root of about 2.7-ish, right? So that's going to be greater than 1. So our function value should be equal to 0 at 1. So we'll have 0 divided by 1 squared, which is 0. And I'm really not sure what happens as, well, actually we could compute the limit as t approaches 0 from the right. This is natural log of t divided by t squared. Natural log of t is going to go to negative infinity. The denominator is approaching 0. So that's actually going to be, whoa, I'm having problems with that sun again. Sorry. I don't know why I'm having all these problems. There we go. So this numerator is approaching negative infinity. The denominator is approaching 0. So this is not an indeterminate form, but basically what we have as t approaches 0 from the right is a very large negative number divided by a tiny positive number. Dividing by a tiny positive number is the same as multiplying by a large positive number. So we've got a large negative number times a large positive number. So that means this is going to go to negative infinity. So I'd expect my graph to go to negative infinity here. So now I'm worried. I'm like, does it go up and then back down? That doesn't seem to make any sense. Maybe I made a mistake somewhere. What is wrong with there's something wrong with the sun, or not the sun itself, the way the sun is interacting with my camera for some reason. It's at a strange angle, I suppose. Negative infinity divided by a tiny positive number should be a large negative number. All right. And we said that f prime looks like this. And then this function is actually equal to 0 at square root of e. We might be interested in this as t goes to 0 from the right. So the numerator is going to go to positive infinity because the natural log of t is going to negative infinity. Then we multiply it by -2. So it's going to be a large positive number divided by a tiny positive number. So a large positive number divided by a tiny positive number is going to be a large positive number times times a large positive number. So we should go to infinity there. I feel like there must be a mistake here. This natural log of t doesn't grow very fast, but it does go to negative infinity relatively fast in the vicinity of 0. So I'm not sure. All right. And then we didn't do this last time. Let's compute the second derivative. It should give us some indication of concavity. So by the quotient rule, we get low, b high. The derivative of 1 is 0. The derivative of -2 times natural log of t is -2 times 1 over t minus high, d low. The derivative of that t cubed is 3t squared. And we'll divide all of that by low. That's t cubed squared. One of those t's will reduce, and what we get is -2t squared minus this expression. If I distribute that 3t squared through the parentheses, distribute that and the negative as well, we get -3t squared minus a negative is a positive, 6t squared times natural log of t. And this t cubed squared, you multiply the exponents, that gives you a t to the 6 there. And then because of the SIGN signs here, we'll have a -2t squared minus 3t squared is -5t squared plus 6t squared natural log of t divided by t to the 6. And we have a t squared in common in that numerator, so we can factor it out. So t squared times 6 natural log of t is that term, minus 5 from that term, all divided by t to the 6th. 2 of the t's reduce, and we've got a t to the 4th in that denominator. So f double prime is 0 when that numerator is 0. So that means 6 natural log of t equals 5, or natural log of t equals 5, 6. So if we exponentiate, t is e to the 5/6 power. And so you say, okay, well, where does f double prime change signs? It changes signs at this x value. We're interested in this function on the interval from 0 to infinity. So we really just need to look at this 6 minus natural log of t minus 5, because we know that t to the 4th is positive all the time, except for when it's 0, but on this interval where t is positive, t to the 4th is always positive. So we just need to figure out where 6 natural log of t minus 5 is greater than 0. Just solve that inequality in pretty much the same way that we solved this equation. Add 5 to both sides, divide both sides by 6, exponentiate, and we get t is greater than e to the 5/6. And when t is greater than e to the 5/6, that logarithm is greater than 0. So we'll get a positive value there, and then over here it should be negative. So the function is going to go from decreasing to increasing. Oops, sorry. This is the second derivative. The original graph is concave down here and concave upward there. concave downward on that interval and concave upward on that interval. And e to the 5/6 power is actually going to be greater than e to the or 1/2 power, because 5/6 is greater than 1/2. So I expect it to be concave down over here on this interval and concave up over there. Let's find the corresponding y value. F was natural log of t divided by t squared. And now for t, we're substituting in that e to the 5/6. Now, with every time you see a log, it's asking you a question. Take the base, you say e to what power is e to the 5/6? It's just 5/6. And then if we square this, we just multiply that exponent by 2. So 5/6 times 2 over 1 is 5 divided by 3. So that's going to leave a 5 in the numerator, and we can put that 6 in the denominator. So that's our y value there at the point of inflection. Provided that I did my arithmetic and my algebra correctly, e to the 5/6 and f of e to the 5/6, which is e to the 5/6 and 5 divided by 6, e to the 5/3. That is our point of inflection. And I still need a calculator to approximate those values in order to graph it by hand. But it should go from concave down on this interval to concave up on this interval. And then based on this sign chart, we know the function should be increasing here and then decreasing here. So let's put those two pieces together. I'm going to graph these three functions. So here's our function. There's our f of t. The interesting things happen there. Now it looks like we've got a relative max over here. And that was at square root of e and f evaluated at square root of e. And when I evaluated f at square root of e on paper, I got 1 divided by 2e. So 1 divided by 2e is this 0.1839 approximately. So we see the same number there. So those are the same value. Now that x value corresponds to the 0 of the first derivative. So let's graph the first derivative. And if we evaluate the derivative at square root of e, we get that value. We see that this first derivative is 0 there. Now we could also graph the second derivative. Second derivative should indicate where the graph is concave upward versus concave downward. And we did some calculations. We got 6 natural log of t minus 5 divided by t to the 4th. Let's try defining t. Oops, there we go. And we said that function is 0 at e to the 5/6. That's my claim, provided that I did my arithmetic correctly, right? So e to the 5/6 is approximately 2.3, and we want to evaluate the function there. That's our function value. Might be a good idea to look at the derivative there. Actually, let's just evaluate the second derivative there. Now the second derivative is supposed to be 0 there. So that is the point when the graph goes from concave downward to the left of it to concave upward on the right. Or alternatively, where the original function goes from decreasing to increasing. Or not the original function, where the derivative goes from decreasing to increasing. So at that x value, e to the 5/6, our derivative should have a relative min, because it should go from decreasing to increasing. So let's evaluate the first derivative there. It's a little bit difficult to see with all those points. But yeah, that seems right. It seems like it's concave down on that interval. Concave down from 0 to that e to the 5/6. And then it's concave upward over there. It seems reasonable. It's a little bit hard to see that it's concave upward, but it seems very reasonable. And then it also looks like the derivative does have a relative min there. It's very difficult to see though. Yeah. But those are our functions. Our first derivative, our second derivative. The relative minimum value, or excuse me, the relative maximum value at square root of e and f square root of e. That's right here. And then the point of inflection was at that e to the 5/6 and f evaluated at e to the 5/6. Okay, so that was one of our functions involving the logarithm. Now let's look at another one. I think we might just do 2 in this video rather than all 4 of these. This is example 7 from our list of functions involving logarithms. We have the f of x is a natural log of the natural log of x squared. We'll do the calculations on paper. Now, because we have the log of a log here, it's just as important as ever that we find the domain. Now, remember, when you're finding the domain of a function, we don't want to divide by 0. We don't want to take square roots or fourth roots or any kind of even root of a negative number, and we never want to take the logarithm of a negative number. So this function is going to be well defined whenever x squared is strictly positive. So we want all real numbers x such that x squared is strictly positive. And I need the natural log of x squared to be strictly positive so that I'm taking the log of a positive number. Now we know that x squared is almost always positive except for when it's 0, right? So if we say that x squared has to be greater than 0, what we're really saying is that x can't be 0. Because as long as x isn't 0, x squared is positive. Now natural log of x squared is greater than 0 when x squared is greater than 1 if we exponentiate on both sides. Now if we look at the graph of y equals x squared, it just looks like this. If we look at that graph and the graph of y equals 1, we can see that y equals x squared is greater than that 1 above that line, above that horizontal line. And that corresponds to these intervals. All the x values from -infinity to -1 map to those y values. And all of the x values from x equals 1 to infinity map to those y values. So this is the set of all real numbers x, such that either x is less than -1, so we're on the far left of the graph, or x is greater than +1. So we can write that in this way. It's the interval from -infinity to -1, union 1 to infinity. So that is our domain. So those are the only intervals we're interested in. And now we'll compute the derivative of this. Now, whenever we compute the derivative, you've got to identify the inside function here because you've got a composite function. Now, sometimes students have trouble with something like this because it looks like you've got 2 composite functions, right? You're like, which one is the outside function? Which one is the inside function? Isn't x squared inside? Well, yeah, but isn't also natural log of x squared inside? Yeah. So you have to sort of pick apart, like, which is the inside function that I should look at first and which is the outside function that I should look at first. When you do this, one of my professors used to say, just stand back and squint and then say what is the outermost function? Like what is on the outside? Like if you just ignore the details, but say what's on the outside of everything? Well, this logarithmic function is on the outside of everything, and the inside function, at least initially, is that natural log of x squared. So when we take the derivative, we identify the outermost function and then the function that's inside of that, and then we use the chain rule. So we say, okay, I'm going to compute the derivative now. What's the derivative of log of a function? Well, we know the derivative of log of a function is 1 divided by that function times the derivative of the inside by the chain rule. And if you want, we can rewrite that expression using our log properties. We know that natural log of a to the n is n times natural log of a. So you can bring that power out front if you want to. So this is the derivative with respect to x of 2 times natural log of x. And that's a relatively simple derivative to evaluate. So we end up with 1 divided by natural log of x squared times the derivative of 2 natural log of x. So we're going to get a 2 times a 1 divided by x. If you want, you can call that a 2 over 1. So when you multiply straight across, you've got 2 in the numerator and x natural log of x squared in the denominator. That is our f prime. You might say, okay, well, when is f prime equal to 0? F prime is never equal to 0. Because you've got a non-zero numerator and you don't have any fractions in the denominator. If you had a complex fraction, like you might be able to flip it and find an x value where that derivative is 0. But since we've just got an expression where there are no fractions, like there is no way that this is 0. If you want to see why that's true, you could just take this equation and try to solve for x. You say, okay, well, how do I solve for x? Well, first let's multiply both sides by this. Then I'll have 2 on this side equals 0 times that on the other side. So 2 equals 0. Like that never happens, right? Since that never happens, f prime is never equal to 0. But we might have some critical values. F prime is undefined when the denominator is 0 and the numerator is non-zero. Of course, in this case, the numerator is 2, which is never 0. This is undefined when the denominator is 0, which means either x equals 0 or natural log of x squared equals 0. And x equals 0 is already solved for x. Here we can exponentiate, and you get x squared equals e to the 0. And that's 1. And so we get x equals plus or minus 1. But x equals plus and minus 1, those are not even in the domain. And x equals 0 is not in the domain either. Our domain is sort of from negative infinity to negative 1, and then 1 to infinity. So these are sort of boundary points for our domain. So those aren't really critical values either. All right. So I guess we can examine the sign of f prime on these two intervals. And we'll rule out all of those x values between -1 and 1 because those are not in the domain. And we'll say f prime is 2, which is always positive, divided by x times natural log of x squared. Now, x is negative on this interval and positive on that interval. This is the interval from negative infinity to -1. That's the interval from 1 to infinity. And then natural log of x squared, well, that's going to be positive when x is greater than 1. Because basically what we're doing is we're looking at this y equals natural log of x graph, and we're substituting a value that's greater than 1. And then if you wanted to, you could say, take this graph and multiply by 2. So when this function is positive, natural log of x squared is positive. Or you can think, okay, if I take a value that's greater than 1 and I square it, well then isn't that going to also be to the right of this 1, and then we get a positive y value? So yes. So we're going to get a positive value there. Now if we're to the left of -1, and then we square it, we're going to have a number that's greater than 1, but positive. So we're actually still going to be in this area. So we're going to have the log of a number that's greater than 1, which is going to give us a positive y value. So we end up, and that's good because we had to take the natural log of that to begin with, right? the natural log of that has to be well-defined, and that's only well-defined when the natural log of x squared is positive. So these are positive. So f prime is a positive divided by a negative times a positive, which is negative on that interval. And then f prime is a positive divided by a positive times a positive, which is positive. So that means our function is decreasing on this interval. So it might look like that. And then it's increasing on this interval. So it might look like that. The concavity might be wrong. It might not be curving up. It might be curving down instead. I'm not sure, but I know it's decreasing. And then from this, I can't tell if I don't know if it's actually going to be concave up and increasing or if it's going to be concave down and increasing, but it's going to be one of those. I know it's going to be increasing from the first derivative. So we've got that. And if we want to, we can find the second derivative of this function by differentiating this function. That's possible as well. I think I want to do that. Let's look at the second derivative. F double prime is the derivative with respect to x of 2 divided by x times the natural log of x squared. And, whoops, having problems with the sun again. So we get, according to the quotient rule, low, d high, which is 0, minus high, d low. Now, d low requires the product rule. My first function is x, and my second function is natural log of x squared. So I'll have derivative of the first, which is derivative of x, which is 1, times the second, undifferentiated, so you leave it alone, plus the derivative of the second. So what's the derivative of natural log of x squared? It's 1 divided by the inside function, because we got a function inside there, right? Times the derivative of the inside. Derivative of x squared is 2x. So that's the derivative of the second, and then we have to multiply by that first function x. All divided by, that's low d high minus high d low over low low. So we're going to have x squared times natural log of x squared, quantity squared. And this x squared reduces with both of those x's, and we end up with 0 times that, which is 0. And then if we distribute the -2, we have -2 times, well, actually, I won't distribute that -2. I've got -2 times natural log of x squared plus 2, all divided by x squared times natural log of x squared, quantity squared. And so that's our f double prime. Now, the denominator is clearly positive all the time. That -2 is obviously negative. And natural log of x squared, well, I think that that's always going to be greater than 2 on our, or excuse me, greater than 0 on our domain, right? Because remember, our domain was defined by requiring that natural log of x squared to be positive because we want to take the natural log of it. So we're interested in this function on the interval from, or on the intervals from -infinity to -1, and then 1 to infinity. We rule out all those x values in between because they're not in the domain. We say f double prime is a -2, which is always negative, divided by this natural log of x squared plus 2. Now that could be negative sometimes, but we're not actually concerned about that because we know that natural log of x squared is positive on our domain. So it's a positive number plus 2 is going to be positive. And of course, that x squared times natural log of x squared squared, we squared everything, right? So that's going to be positive and a positive there. So this is a negative times a positive divided by a positive, which is negative. And we have the same sign on this interval. So the graph is concave down here and concave down here. But remember, the original function was decreasing on -infinity to -1, and then increasing on positive infinity to 1. So when I graph it, when I say it's concave down on this first interval, it's concave down and it's decreasing. So I just look at the part that's decreasing on the concave down graph. So its graph locally is going to look like that. And here on 1 to infinity, the function is increasing, but the graph is concave down. So it's going to be like that. So that's the part of the concave down graph that's increasing. So I expect that behavior on our graph of the natural log of x squared. All right, so we know when the function is decreasing, we know when it's increasing, we know when it's concave downward, which is all the time. We've got 2 branches, and we might want to actually look at that function And we don't have any relative extrema because our function is just defined on these two intervals. So we have natural log of a positive number here, and then I think I would just expect like two branches that have the sort of right behavior. I'm not actually sure, but I know I should have vertical asymptotes at -1 and 1. So I'm trying to infer what would the graph look like. I'm like, I don't really know. Here's x equals -1. Here's x equals +1. And we know in this interval, the function is a concave downward and decreasing. And on this interval, the function is concave upward, or excuse me, concave downward and increasing. And I expect it to look something like a logarithmic graph, which has that basic shape. So let's look at the graph on Desmos. And I'm focused on that function there. So there's our graph. All right, we see something that looks a little bit like a logarithm. It's got that sort of logarithmic shape. It's a little bit steeper than I might expect here. We've got vertical asymptotes at x equals ±1. And then our first derivative is 2 divided by this x times the natural log of x squared. And it has the same formula on the other side. We see the second derivative, or the first derivative, excuse me, is negative here where the function is decreasing. The function is, or the first derivative, that's the green graph, is positive when the purple function is increasing. Then we want to look at that second derivative on those same intervals. And the second derivative turned out to be a little bit more involved, right? It was -2 times natural log of x squared plus 2, which is positive on the interval of interest, all divided by x squared times natural log of x squared squared. Now we're only interested in the branches where x is less than -1 or greater than +1. So this stuff in the middle for this function is not of interest to us, at least not when we're talking about the second derivative of the original function, because those branches are not in the domain. So that's our f double prime on 1 to infinity, and f double prime on -1 to infinity. So our second derivative is negative here. So our original function is concave downward. Second derivative is negative here. Original function is concave downward. So that just means if our second derivative is negative, that means our derivative function, that is the green function, is decreasing. Nothing particularly interesting there, actually. But we did the calculations and it's consistent with the original function. The original function was concave downward and decreasing here. And that the original function is that purple function, right? It's concave downward and increasing on this interval. For our eighth function involving a logarithm, we have this. Now remember, if we have the log of a quotient, we can write that as log of the numerator minus log of the denominator. So this is actually log of that square root of 2 plus x squared minus log of x. And then we can write that square root as a 1/2 power. And you can bring the 1/2 out front. It'll make it a little easier to compute the derivative. Now I forgot to compute the domain. and I used a property there. The nth root of x to the m is x to the m divided by n. So the index of the radical goes in the denominator. That's what we did there. There's an implied 2 there and an implied 1 there. And then here we just use this property, log of a to the n is n times log of a. So you can bring that power out front and we get this. Now when we compute the domain of this function, we need this expression inside that logarithm from the very beginning version, before we manipulated it. We need that to be positive. Well, the square root in the numerator is always positive. So we're just concerned about that denominator x being positive. So our domain comes from setting x to be greater than 0, or we're going to have a domain of 0 to infinity. And so we know that that's true. And then this is our simplified form of f. So if we want to, now we can compute f prime. This is just a constant times a logarithm. So you've got your constant times the derivative of that logarithm. And that logarithm has an inside function. It's got that 2 plus x squared inside. So the derivative is 1 divided by the inside function times the derivative of the inside. And the derivative of the inside is just 2x. That 2 in the numerator reduces with that 2 in the denominator. You can write that as it's x divided by 1. So you can multiply straight across. You get a single fraction there. And then you're subtracting 1 over x, the derivative of natural log of x. Now, usually to simplify our calculations, when we set f prime equal to 0 and solve for x to find those critical points, we get a common denominator. The least common denominator, when the two denominators don't have anything in common, is just the product of those denominators. So this denominator is missing a factor of x if I want to have a least common denominator of x times 2 plus x squared. So I multiply this one by x, divided by x, so that my new denominator has that x times the 2 plus x squared in it. Now on this one, the missing factor is that 2 plus x squared. So we multiply by 2 plus x squared divided by itself. And now these two expressions have the same denominator. It's just that x times the quantity 2 plus x squared. And we can subtract the numerator. So we've got x times x there. And then we'll subtract the quantity 2 plus x squared. The x squareds reduce and we just end up with a negative 2 in the numerator. Now, on the interval from 0 to infinity, x is always positive, 2 plus x squared is always positive because it's always greater than or equal to 2, right? And the negative 2 is always negative. So if this is positive, and that's negative, f prime is negative on the domain. So that means the original function is decreasing all the time. You'd say, okay, well, it doesn't have any extrema, but we know it's decreasing the whole time. What else do we know? Is it concave upward or concave downward? Well, in order to figure that out, we'll take the second derivative. So we've got the derivative with respect to x of this negative 2 divided by x times 2 plus x squared. Now, if you want to, you could bring that up to the numerator, both of those. You could call that an x to the negative 1 times a 2 plus x squared to the negative 1 times the negative 2, and then just use the product rule with the chain rule. I'd rather use the quotient rule. The derivative of a quotient is low d high, which is 0. And whenever you use the quotient rule with a constant in the numerator, one of those terms in the numerator is going to reduce. It's going to cancel because you're multiplying by a 0. So it's low d high minus high. D low requires the product rule now. So this is our first function, and this is our second. So we'll have derivative of the first, which is 1, times the second, which is that 2 plus x squared, plus the derivative of the second, which is 2x, times the first, which is just an x. All of that is divided by low, so you square each of these factors in the denominator and multiply them together. And this guy, when you multiply by 0, gives you 0. So you end up with a positive 2 times this expression in the print or in the brackets. We got 2 plus x squared plus 2x squared. And we can collect like terms. It's going to be 2 times 2 plus 3x squared, all divided by x squared times 2 plus x squared quantity squared. Say, okay, we're on the interval from 0 to infinity. Sorry, there's a weird glare again. So this is positive, this is positive. X squared is positive, so I multiply by 3, it's still positive. Add 2, well, it was non-negative before. Then we add 2, then it's greater than or equal to 2, so it's positive. So all these factors are positive. So f double prime is positive on 0 to infinity. So that means that our original function f is concave upward the whole time. Now, when I draw my sort of representative graph for concave upward, it looks like that, but we want it to be concave upward and decreasing. So we're going to be on a part of the graph that looks like this. I don't know if I did that correctly. It just doesn't seem intuitively correct that the graph would look like that. Maybe I made an error. We'll see. Let's look at these functions, the first derivative, second derivative, and the original function, and see what the graphs look like. So this is our original function. It has a vertical asymptote at x equals 0. And it actually goes to positive infinity rather than negative infinity. The function was supposed to be decreasing because f prime is always negative, and the y values on the graph of the derivative are always negative, so that's consistent with what we see. We look at the function values themselves. We go from left to right, the y values go down, so that the function is decreasing. It's consistent with the first derivative. And then if we look at the second derivative is always positive. So that means the graph is concave upward, and that's consistent with what we see as well. So yeah, this is a decreasing function that's concave upward, and the first and second derivative reflect that. So cool, that was relatively easy. And then this is our last function for this video. We're gonna look at the natural log of the quantity x plus the square root of 4 plus x squared. This is actually an antiderivative that comes up when we study trigonometric substitution in Calculus 2. So I'm kind of interested in what that derivative looks like. Okay, so this is our f of x this time. And we're going to do the same thing that we did in the last few examples. We're going to look at f prime, we're going to look at f double prime, and we're going to think about the domain before we even do that. So the domain of this is a set of all x values that are real, such that x plus the square root of 4 plus x squared is greater than 0. Now the key with this, figuring out that interval, is, well, you can either just solve the equation for the x values. It's actually an inequality for the x values by moving that root term to the other side, squaring both sides, and then doing some algebra, trying to figure out what x is, and then taking out any x values that cause, this expression to be undefined. Actually, that expression is well defined all the time. You could do all of that, or you could just think about this square root of 4 plus x squared. That 4 is going to be relatively insignificant when x gets really large. So this is just going to be slightly greater than a square root of x squared when x is large. And the square root of x squared is the absolute value of x. If x is positive, we just get x back. If x is negative, then we get the absolute value of x. So if I substitute -3 here, -3 squared is +9. The square root of 9 is +3. So we get the opposite sign when x is negative here. This is always positive, but we could plug in a negative value here and get a positive answer out. So we see that this is true, and we know that the absolute value of x is x when x is positive or 0, and it's -x when x is negative. Of course, it's just itself when x is positive or 0, and then if x is a negative value, we multiply by -1 to get a positive answer for that absolute value of x. So with that in mind, on the interval from 0 to infinity, or excuse me, -infinity to 0 when x is negative, what that inequality says is that the square root of 4 plus x squared is greater than -x. So if I add x squared to both sides, or add that x to both sides, I get on the interval from -infinity to 0, this expression is positive. And of course, if x is greater than or equal to 0, I've got a positive number plus a positive number, which is positive. So this is actually positive all the time. So the domain is all real numbers. So we'll say that's true, and then obviously when x is greater than 0, the square root of 4 plus x squared plus x is greater than 0. So the domain of f is all real numbers. Okay, so we know that that's true. All right. Now, when I compute the derivative of this, I'm going to use the chain rule. So I've got the log of a function. The derivative of log of a function is 1 divided by that function by the chain rule, times the derivative of the inside, also by the chain rule. And we remember that the square root is actually the 1/2 power. So this is 4 plus x squared to the 1/2. Now when I compute the derivative of this, the derivative of x is just 1. And the derivative of this piece requires the chain rule. Again, because I've got an inside function, that 4 plus x squared is in that square root function, or that 1/2 power function. So we'll take the derivative of the outside first. We get 1/2 of the inside function to the negative 1/2. Then we put the inside function back inside, and then multiply by the derivative of the inside by the chain rule. Then this 2 and that 1/2 reduce, and you just end up with an x times that 4 plus x squared to the negative 1/2 power. So this gives us 1 plus x divided by the square root of 4 plus x squared. And that's because I've got that x squared, 4 plus x squared to the negative 1/2. That's the same as 4 plus x squared to the positive 1/2 in a denominator. And that's the positive 1/2 power is a square root. And we're taking all of that and dividing by x plus the square root of 4 plus x squared, because that was our denominator here. So this goes in the numerator, and we tried to simplify it first. And then the original denominator from that 1 over the inside function goes there. And you say, I've got a fraction within a fraction. I don't want that. So the one way we can get rid of that is we can multiply by the least common denominator of all of those fractions within a fraction. Well, the only denominator from those list of smaller fractions is this one. So I'm going to multiply this by square root of 4 plus x squared. That's the least common denominator of all those denominators. That's legal as long as we do the same thing in the denominator here. Now, if we distribute in the numerator, but don't distribute in the denominator, just leave the denominator alone, turns out we see a cancellation. This 1 times that square root is the square root of 4 plus x squared. And then this fraction times that square root, when we do that, the square roots reduce, and we just end up with a plus x. All of that is divided by x plus the square root of 4 plus x squared times the square root of 4 plus x squared. And we say, hey, look, there is a common factor in the numerator and the denominator. This expression and this expression are the same because a plus b is the same as b plus a, right? Or addition is commutative. So that divided by that is 1. And what we end up with for our f prime is this 1 divided by the square root of 4 plus x squared. Or if you prefer, you can call that 4 plus x squared to the negative 1/2 power. Now, when it's written like this, it's obvious. It's the positive 1 divided by a positive square root. So this is always positive. So the derivative is always positive. That means the original function is always increasing. And the domain was all real numbers. So the function is increasing on R. As we go from left to right, the y values just increase on this graph. You say, okay, well, what about concavity? If we're interested in when the graph is concave upward versus concave downward, we need to take the second derivative of this function. The second derivative of this function involves taking the derivative of the first derivative, so we'll take the derivative again. Get the second derivative here. So we're taking the derivative with respect to x, sorry about the weird glare again, of 4 plus x squared raised to the negative 1/2 power. That requires the chain rule, because you've got a function inside that negative 1/2 power function. So when we take the derivative, we're just going to use the power rule. Bring the power down, multiply by the inside function to the 1 less power. Negative 1/2 minus 1 is the same as negative 1/2 minus 2 halves or negative 3 halves. You want to put the inside function back inside and then multiply by the derivative of the inside. The derivative of 4 is 0 and the derivative of x squared is 2x. So the 1/2 and the 2x reduce, or the 1/2 and the 2 reduce. So we end up with a negative x in the numerator. And then we have a 4 plus x squared to the 3 halves in the denominator. Sorry about the weird glare again. I don't know why it's giving me that glare. That's a 4 plus x squared to the positive 3 halves in the denominator. Or if you prefer, you can write it with radicals. That 2 in the denominator means we're taking the square root of 4 plus x squared, quantity cubed because of that 3. Okay, so f double prime is this negative x divided by that. And f double prime is 0 when the numerator is 0 and the denominator is non-zero. Now the denominator is always positive because x squared is always non-negative. You add 4 to it, then it's greater than or equal to 4. Then you cube it, so it's going to be greater than or equal to what, 64? And then you take the square root. Anyway, it's positive. So this is positive, and then this numerator is 0 when x equals 0. So f double prime is 0 when the numerator is 0, which means that x equals 0. So that is a potential point of inflection. And if we make a sign chart for f double prime with the only potential point of inflection on it, we see that we've got negative x divided by this. And this expression is always positive. It doesn't matter what x is, it's going to be positive. Now, when x is positive here, we have a positive number times a negative, so we're going to get a negative. And when x is negative, we have a negative times a negative, which is positive. So f double prime is a positive divided by a positive, which is positive, and on this interval. And then it's a negative divided by a positive, which is negative. So the graph is going to be concave upward here and concave downward here. And the function is increasing the entire time. Since it's increasing the entire time, I sort of select the parts of this concave upward parabola where the function is increasing. So the function is increasing in concave upward like there, and the function is increasing in concave downward there. So our graph is sort of locally going to look like that until it reaches that point of inflection at 0, and then it's going to look like that. So the natural log, or y equals the natural log of x plus the square root of 4 plus x squared. It has a point of inflection. And it's going to be 0, and then this function evaluated at 0. Natural log of square root of 4 is just natural log of 2. So at x equals 0 and y equals 0.69 approximately. I think it's 693, but I'm not sure about that third digit. So that's our point of inflection. The function's increasing the whole time, and it's concave upward on this side. And then it's concave downward on this side. See how I tried to draw it like that, concave upward but increasing? And I tried to draw it like that, concave downward but decreasing. I think that's my graph of y equals the natural log of x plus the square root of 4 plus x squared. And let's look at that on Desmos. And then I think we'll be done. We'll be done with our, at least these examples of functions involving the logarithm and their graphs. So that's the argument that x plus the square root of 4 plus x squared is always positive. So the function natural log of that expression is well defined for all real numbers. It does look like it's increasing all the time. And then if we evaluate it at 0, yep, there's that 0.693, that natural log of 2. And it looks like it's concave upward on this side and concave downward on the other side. Let's look at the derivative. The derivative should be positive the whole time, right? And it is. Looks like it has a maximum somewhere in here. Yes, it should have a maximum at the point of inflection, right? So let's evaluate the derivative at 0 as well. So it has a value of 1/2. That makes sense. I want to change my, change my range of y values. Let's like zoom in a lot. That looks a little bit more interesting, right? We zoom in a lot, we sort of exaggerate things. If we have our y values between -4 and 4 and our x values between what, about -9 and 9, if we're going from -3 pi to 3 pi. But now we can see that concave upward here, concave downward here. The derivative is increasing, then it has a relative max of 0.5 at 0, then it's decreasing. So when the derivative goes from increasing to 0, having a 0 slope to decreasing, that's when the original graph should go from concave upward to concave downward, which is what we see here. And we can also see that if we look at the second derivative. The second derivative is 0 at 0, and it's positive over here. So the original graph is concave upward, and then it's negative here. So the original graph is concave downward. And we also see that the first derivative is decreasing when the second derivative is negative. And the first derivative, the purple graph, is increasing when the second derivative is positive. So we can see that the concavity and the the concavity of the first graph, that orange graph, is indicated by both the fact that the sign of f double prime and the increasing and decreasing nature of f prime. And then we can also see how the increasing and decreasing nature of f prime relates to that green graph as well. Actually, I think I just repeated what I just said. Anyway, we can see how all those derivatives are related to each other. I think that that's pretty cool. All right, so we're done. That's the graph for example 9. In another video, we might do some more with these graphs, looking at extrema of functions involving logarithms. I'm using the first and second derivative as well. But that's it for this video.